Have you ever pondered upon the question, what is the nature of mathematics and where does set theory fit into it? Mathematics, in its essence, is a language of abstraction, a tool to decode the universe's patterns. Set theory, an integral part of this language, lays the groundwork for nearly all mathematical disciplines. It's like the atomic structure that forms the basis of all matter. Today we delve into the fascinating world of set theory, its paradoxes and the profound impact it has had on mathematics. Set theory, simply put, is the study of collections of objects that we call sets. Let's think of it this way. If you have a bag of apples, the bag is the set, and the apples are the elements. The elements are the individual objects that make up the set. So if you have a bag with a red apple, a green apple, and a yellow apple, you have a set of 3 elements. Now let's say you have another bag, but this time it contains only red apples. This smaller bag is what we call a subset. A subset is a set that is entirely contained within another set. So the bag of red apples is a subset of the bag of apples. But what if we have 2 bags of apples? One with red apples and the other with green apples. If we were to find the common elements in both bags, we'd find none because red apples aren't green. This lack of common elements is what we call the empty set or null set, symbolized by the Greek letter phi. On the other hand, if we have a bag of red and green apples and another bag of red and yellow apples, the common elements or intersection would be the red apples. This is where the fun begins. Intersections are the elements that 2 or more sets have in common. In our example, the intersection of the 2 bags would be the set of red apples. But what if we want to consider all the apples in both bags? Well, that's where the union of sets comes into play. The union of 2 or more sets is a set that contains all the elements from all the sets. In our case, the union of the 2 bags would be a set of red, green, and yellow apples. And there you have it. That's the beauty of set theory. It's all about understanding how different groups of objects relate to one another, and it forms the basis for a lot of mathematical thinking. So, that's the basics of set theory. But things get more interesting when we dive into its paradoxes. A paradox, in essence, is a statement that contradicts itself. In set theory, paradoxes challenge our understanding of mathematical logic. Now let's dive into the world of paradoxes in set theory. These logical contradictions have been rattling the foundations of mathematics for years, leading to profound insights and advancements. 2 of the most famous paradoxes in set theory are the Barber paradox and the Russell paradox. Let's take a moment to explore these paradoxes. The Barber paradox is a self-referential puzzle. It revolves around a barber who shaves everyone in town who doesn't shave themselves. The paradox arises when we ask the question, who shaves the barber? If the barber shaves himself, then by definition he doesn't. Conversely, if he doesn't shave himself, then he does. This paradox highlights the difficulty of self-reference in set theory. Next we have the Russell paradox, named after the British philosopher and logician Bertrand Russell. This paradox challenges the notion that any definable collection can be a set. In simpler terms, consider a set of all sets that do not contain themselves. Does this set contain itself? If it does, then it doesn't. If it doesn't, then it does. This paradox exposes a flaw in the naive set theory, leading to the development of more sophisticated mathematical frameworks. These paradoxes, while perplexing, have served as catalysts for the evolution of set theory. They have forced mathematicians to reconsider the foundations of mathematics, leading to the development of axiomatic set theory. This theory attempts to build mathematics on solid footing, free from paradoxes. Furthermore, these paradoxes have also contributed to the philosophy of mathematics. They have provoked deep questions about the nature of mathematical truth and the limits of our logical reasoning. In conclusion, the paradoxes in set theory, while initially appearing as roadblocks, have played a crucial role in shaping the landscape of mathematics. They serve as reminders of the inherent complexity and beauty of mathematical logic. These paradoxes have perplexed mathematicians for centuries and have significantly influenced the development of set theory. Mathematicians have made numerous attempts to resolve these paradoxes. In the early 20th century, one of the most notable attempts to address these paradoxes came from 2 mathematicians named Ernst Zermelo and Abraham Fraenkel. They proposed an axiomatic system that aimed to avoid the paradoxes that had troubled set theory. Zermelo and Fraenkel's axiomatic system, often abbreviated as ZF or ZFC, with the C referring to the axiom of choice, forms a solid foundation for most of mathematics. It's like building a house. You start with a strong foundation and build up from there. Zermelo and Fraenkel provided that foundation for set theory. They introduced a number of axioms or rules that sets must follow. These axioms were carefully chosen to avoid the paradoxes we've discussed. For example, one of the axioms, known as the axiom of regularity, prevents the creation of sets that contain themselves, thus avoiding the Russell paradox. ZF or ZFC is widely accepted among mathematicians. It has provided a framework for much of modern mathematics and has been instrumental in our understanding of sets. But it's not a perfect solution. Some mathematicians argue that it's too restrictive and there are still questions it can't answer. Despite these efforts, set theory still faces unsolvable challenges. But remember, in mathematics, a challenge is not a dead end, but rather a door leading to new possibilities. Who knows what exciting discoveries await us beyond these paradoxes? The paradoxes in set theory have not just been obstacles but also catalysts for growth in mathematics. Just as a pearl forms around a grain of sand, sometimes it's the irritations, the problems, the paradoxes that stimulate the most brilliant advancements. Set theory, despite its paradoxes or perhaps because of them, has profoundly influenced other areas of mathematics. For instance, the theory of functions, a core component of calculus, relies heavily on the concept of sets. It's through set theory that we can define a function as a set of ordered pairs, where each first element is related uniquely to a second element. Set theory also underpins the concept of number systems. The natural numbers, integers, rational numbers, real numbers, and complex numbers are all built using set theory. Without sets, we wouldn't have a solid foundation for these fundamental building blocks of mathematics. Moreover, set theory has been instrumental in the development of mathematical logic and proof theory. The paradoxes of set theory presented challenges that mathematicians had to overcome, leading to more robust and comprehensive logical systems. One of the most significant contributions of set theory to mathematics is the concept of infinity. Before set theory, infinity was a vague, undefined concept. But with German mathematician Georg Cantor's work on set theory, infinity became a concrete, workable mathematical concept. Cantor's work led to the creation of transfinite numbers, a whole new way of thinking about infinity, which has had far-reaching implications for fields as diverse as physics and philosophy. In conclusion, set theory, much like the skeleton in the human body, provides the structural framework that supports and shapes the body of mathematics. It's the language that allows mathematicians to communicate complex ideas clearly and precisely. It's the tool that enables us to define, categorize, and understand the mathematical universe. Thus, set theory, with all its paradoxes, continues to be a fundamental part of the mathematical world. Paradoxes, despite being unsolvable problems, serve as powerful thought experiments in mathematics. They are like the riddles of the math world, teasing our minds and challenging our preconceived notions. When we encounter a paradox, we're not just facing an unsolvable problem. We're facing a challenge that forces us to rethink our assumptions. It's as if we're walking down a familiar path, only to find that the road has been replaced with a maze. We can't move forward using our usual methods. Instead, we have to take a step back, reassess, and find a new way forward. Consider the barber paradox, for example. It forces us to confront the inconsistency in our logic about who shaves the barber. No matter how we try to answer, we end up in a loop. This paradox isn't just a quirky riddle, it's a mirror that reflects the limitations of our logical system. Then there's the infamous Russell's paradox. It's like a mathematical cliffhanger, leaving us in a state of suspense. The problem lies in the concept of a set containing all sets that do not contain themselves. Does it contain itself, or not? This paradox compels us to reevaluate our understanding of sets, leading to the development of new mathematical structures and theories. These paradoxes, these unsolvable problems, they're not roadblocks. They are catalysts for innovation. They push the boundaries of our understanding, forcing us to invent new concepts and redefine old ones. They're like the mathematical equivalent of an explorer charting uncharted territory. In the end, the paradoxes in set theory remind us that even in the precise world of mathematics, there are mysteries waiting to be unraveled. And though we may not solve these paradoxes, we can still appreciate the journey they take us on. After all, it's not just about finding the right answer, but also about asking the right questions.